to go into the list for looking for element. If I know the index value, I know exactly where to go to right away. So in terms of finding the elements, let's say I'm going to draw this as another list array. I don't care, memory. Before, if this was in, I have to go from top to bottom, try to find the element. But if I know there's something called index values, I know where it is right away. If I know the index values, I can get out the elements right away. A, B. What is the time complexity of finding a value here? Searching cost, 1, constant. 오, 오늘 굉장히 평소에 거의 1년 만에 보여주는 모습입니다. 이렇게 당황스럽게. 너무 집중하지 마. Index. So search cost of this dictionary or something like this, probably constant. That's the basic idea for hashing as well. So later, if I draw a hash example, I'll probably draw exactly the same, but name is slightly different. So having that in the mind, this is something called dictionary, a similar data structure, a bit more sophisticated data structure. So dictionary is, as we know, is a collection of elements. Each element has a field called key. Key. So in a similar way, index here as a key. So at this point, you can think of database as well. I mean, similar ideas. So every element has a key and its own value. So if I'm looking for something, I ask for whether you have that key. If they have the key, return the value. That's a simple procedure being done here. Every key is usually distinct. So I can find out, hopefully there is no duplication. If there's a duplicated key, then I don't know which one to look for. I don't know which value am I looking for, right? So typical dictionary operations are determine whether or not dictionary is empty. That is probably similar to the empty function of any data structure that we have looked so far. I mean, queue stacks, everything had a empty operations. Determine the dictionary size. How many elements do I have at this point? Similar to size operation on any ADT that we have looked for. Insert pair into a dictionary, likewise. But you have to remember that you have to insert a key and its value as well at the same time here. So search, delete is likewise. So I actually brought up this is if you look for Python, some stuff, I like to find out how to use a Python and stuff like that. Then it's a website that you can look for. And Python also provides something called dictionary itself. And see what, they actually have all kind of queue examples as well, using list as a queue. They explain how to use a queue that we studied in Python ways. So if you don't know where to start, you can just copy and put that in your program that we will do. So in here, I'm looking for a stack이란다. Dictionary. Dictionaries. Blah, blah, blah. They explain pretty much what I just described. They start explaining the key functions, sorted, and let's take a look at the example here. So they define something, dumb dictionary called tel. I don't know what that is. Maybe telephone number. So key here, it will be a jack. Value of a jack is 4098. So that's probably telephone number, extension numbers of that. So you can see that single part have a key and value itself. And then you try to look for a telephone number of some guy named, 여기는 없는데? You try to add some guy named, I don't know how to pronounce it, Guido. And his phone number is 4127. This will be added into the list as well. Later, if you want to find out the phone number of a Jack, you're just looking for Jack. then they will give you the 4098 right away. Okay? It's a very easy example on dictionary on Python. I don't remember if I ever used the dictionary function in C, but Python is much simpler in terms of using it. So in a way, they also like tell this dictionary what's a Jack's value right there. Also delete the key of a safe. Some safe? I don't know. Delete the function. Adding a function, just simply declare like array and give it the value. In the array, we usually give a 0, 1, 2, 3 inside this bracket, right? But in here, we can give a key. So that's a very simple example on how we can actually use a dictionary in practice. So you're welcome to do it. Where you can use a dictionary? I don't know. We'll take a look. Let's take a look at some other examples later on. Anyway, you can look for something like this. There's billions of websites explaining how to use this type of data structure. This is just a Python examples. But Python is simpler because it's just quite similar to what we have written in our slide. Other programming languages is a bit difficult for first-timers to jump in it. So that's my recommendation. Do take a look at it. 쉽죠? Dictionary is quite easy. Giving a key. We have seen search, insert, delete from those Python dictionary examples. Accessing dictionary elements. You can access dictionary from top to bottom because it's a list. So if you don't know the keys, you don't know the values, you can just simply ask to print out everything, whatever that is, which order they have it, it doesn't really matter. You can just ask them to give a complete list of a dictionary elements. Random access. Any elements in the dictionary can be retrieved by simply performing a search on its key. We give a key, get the value. They're referring to as a random access. That's assuming that we know the key. There might be other situations like I give them a key, but the key never been received in the dictionary. Then dictionary should report that I don't have that key. Okay, make sure. Or you're asking the empty dictionary for a key. So things like that should be a careful categories that you have to check. Sequential access. Elements are retrieved one by one, ascending order of the key field. Just get the key, every single key in the list, just get them out, the values out. There are other ways of doing it. Sequential access operations begin next, retrieve the elements with the smallest key, retrieve the next elements, and this is just one of the examples, just getting everything out of the list, dictionary for elements. Dictionary with the duplicates. Keys are not required to be distinct. So you may have a duplicate keys, but you have to come up with a way of how to solve the situations. Word dictionary, for example, is pair R of the form word meaning may have a 2 or more entries for the same word. For example, meaning of the word ranking. So in a English dictionary, you look for a one vocabularies, they may have a multiple meanings, right? It means that the word itself is a key, the value may be different. So that's also allowed of doing it, but typically I don't want a situation that have a duplicate keys, but they just give you example on dictionary can have a duplicate. Is this possible in database? Unique keys. Probably not something that you desire to have. Applications of dictionary. We have seen very simple applications of dictionary in Python documentation files. Collection of the student record in class, key value, student number, student ID, to assignment or your exam mark. In this case, student ID is all distinct, right? So I know many of you taking the database at the same time. If you implement the database itself, then dictionary might be one other way of doing it, right? Assuming that you try to build a very simple database. Dictionary is a data structure behind of it, indexing the large elements in the system. Get the element whose key is tiger whoops. It's a golf. I know you guys don't play golf anyways. Exercise, give the real word application of dictionary and dictionaries with the duplicates. We know all this. I mean, they already give the English dictionary have a single key with the multiple meanings. That's one example. Other examples. Well, pretty much everything can have a dictionary itself. Again, why we wanted to have this dictionary implementations? We like to shorten the search time. It's easier to search. Just give a key, get the value. Instead of giving a binary search function keys, try to look for that. Constant. Beauty of hashing later on. You can certainly take a look at the ADT for dictionaries, abstract classes of a dictionary. If you're really lazy, then you can type on Python dictionary on Google. They probably give you similar definition itself too. But they probably don't call itself as ADT, just the operations. If you declare dictionary, how to use it. Okay. The functions are pretty much same. The name slightly different, but what they do is pretty much same as we looked at. 아이고, 많기도. 똑같은 얘기인데. Dictionary as an ordered linear list. Linear list we know, order we know. Each element is a pair key and value. So each element in key and value. Key, value, pointer. Key, value, pointer. You can do this too. Array or chain representations, right? Every data structure that we have looked at so far, they have at least two ways of implementing. Because we've been just discussing mostly a list, right? Either array-based representation or a linked list way of doing it. So unsorted array, let's see, sorted array, unsorted array, unsorted chain, assorted chain. We all know that by now. I mean, in case of chain, that doesn't really matter. The worst case, we have to look for every n elements. If it's implemented on top of array, you could try a binary search on it as well. So that's why the second line, sorted array, you can try a binary search, give you order of log n search time. It's pretty much straightforward. I'm just telling you that dictionary can be implemented that way as the chain it is, or array. I don't need to go into that. So I was always thinking whether we should discuss the dictionary before the skip list, but it's just give you idea of having this type of data structure is helping you to. My experience, if I use a dictionary, my code is much more cleaner because I don't need to implement a bit more complex functionalities in my code. So I simply use a dictionary. But if you're dealing with a very large number of data, dictionary might not be the way of doing it. 그냥 뭐 숙제하고 이렇게 편하게 할 땐 딕셔너리를 하면 되게 편하거든요. 코드가 짧아져서 또 다 돼 있잖아. 뭐 체인에 add하고 이럴 것도 없으니까. how do you add an element in chain? We know that you have to go into pointer, you change the pointer. I mean, those type of steps we don't need to do if we're using a dictionary. I mean, it also depends on the cases, but again, if you're dealing with a very large number of data, then dictionary might not be the way of doing it because it may slow comparing to do it yourself. Okay, skip list. Going back to the skip list. Skip list improve the performance of insertion and deletion operation. Why? Again. I can skip some of the elements. Before, if I wanted to add an element to the end of a chain, end of a linked list, then I have to go n times and add an element. But this time, if I know there's an additional forward pointer, maybe I can go half, that reduce number of elements that I have to go to by n divided by 2. Or if there's a fast pointer to the end of a list, like a circular linked list, then moving time is just 1. Right? So it's improving performance of insertion and deletion operations. Employ a randomization techniques to determine where and how many put additional forward pointers. How do you determine how many pointers should we add into the list? I mean, they probably give you levels later, adding an additional pointer to every single element, every other single element, and then half of that list. So how to make those decisions? They call it as randomization techniques. It's not so clear. Sometimes they just do a random ways, adding a pointer to it. Expected performance of a search and deletion operation on skip list is order log n. Expected. That's something that we wanted to have by adding an elements, adding an additional pointer to a list. So hopefully we can achieve as much as using a binary tree like. However, worst case performance is still order n. Why? Worst case, I have to go through every single element. I mean, the pointer, maybe I skip one of the elements by accident, taking the fast pointer out of it. This is the picture of a very simple picture of a skip list. 도대체 내가 몇 페이지를 하고 있는지 알 수가 없네. 보이지가 않아요. Skip list, pointer, search, and insert. So pointer to a middle edit. I decided to put a pointer just halfway to the list. That give me a luxury of skipping this first half. So I can do something like binary search too. If I know the value of what's in the middle, and the value I'm looking for is greater than value in the middle, then I can take this pointer up and I can start looking for one by one from this point on. It means that I just skip the half, right? Hopefully that fast up the process for searching for elements. Pointer to every second element node is edit. Every second element, so one here, another one here, another one here, like that. Okay. Last pointer encounter when searching for 77. Last pointer is searching for 77. I don't know. I can go this way or pointer. Let's see. If I'm looking for 77, I look for value 40, but 40 is smaller than 77. It must be on this way. So I can go from this point, I can go check out this every second pointer, 75. 77 is still bigger than 75, so I can move one here, but it's not there. Something like that. Those type of searching operation is possible. 지금 뭐 이렇게 갔다가 먼저 중간에 있는 거 먼저 보고 갈 수도 있고 안 갈 수도 있고 이렇게 여러 가지 방법을 할 수 있죠. The last one is saying that if there is no 77, I can find out where to add a 77. Probably right next to 75, because there seems to be no number between 75 and 80. If you try to add that up, then you might need to change the pointer operations too, right? 포인터도 바꿔야 되겠지? 바꾸면. So a bit more complicated way of doing it, but skip list, it gives you idea of how to adding a pointer to this. Fast searching of a sorted chain. Okay. Dictionary as a skip list. Read example 10.4, see figure 10.1. A sorted chain with the head and tail nodes adding a forward pointer search and insert operation is skip list. Basically, key value. Dictionary had the key value, right? So if I have a sorted key into this skip list, hopefully I can just looking for keys. If it's a bigger, then I go to the next half. If it's smaller, I go back to the first half, go into the smaller pointers, lower level pointers to searching for elements. So you can use the skip list to implement a dictionary. Like probably not as a order of constant like hashing, but hopefully it's much faster than order n approach. For general n, the level 0 chain includes all elements. So level 0 at the bottom. 어디 갔니? Level 0 at the bottom have every element. Level 1, every second element. Level 2, 2 for every fourth element, like that. So they can give you the levels of adding a pointer to it. 0, 1, 2, 3 이래서 0일 때는 다 하고 1일 때는 2개, 2일 때는 4개, 3일 때는 몇 개 해야 되니? 8개? 뭐 그런 식으로 pointers. So that's what it says. For general n, level 0 has include all elements. Level 1 chains include every second elements. Level 2 chains include every fourth elements. Level I chains include 2 to the ith elements. 2의 3승, 2의 4승 elements. Adding a pointer to it. And elements in level I, level I elements, if and only if it's in the chain for levels 0 to through I. It's okay. You don't need to understand 100%. That just reminds me of a three-dimensional matrix. 아니야, 뭐지? For the midterm questions, what was the question for the 5차원이었니? 5-dimensional row major column ordering, 그죠? I've seen very many creative answers for that questions. I guarantee you there is no partial mark on that part. 그거는 부분 점수를 줄래 줄 수가 없더라. 희한한 식들이 많아서. A similar idea is built on this. 이거를 다 하면 안 되는데. 다 해버릴까? 다 해볼까? 뭘 쉬어? 할 게 있어야 쉬죠. 방금 전에 그 눈을 초롱이면서 질문하더니 딱 30분이 지나가니까 눈을 아예 닫기 시작했어요. 그렇지 뭐. 한 달만 더 버텨. 한 달이면 또 끝나는데. 한 달이면 2학년이네. 그렇죠? Okay, hash table. Going back to this. I'd like to build some type of list with search function of constant operations. Hash table is an alternative method for representing a dictionary. We could represent a dictionary with the skip list or hash table. And hash table, hash function is used to map the keys into position into a table. This act called hashing. So example that I give you for that dictionary is more appropriate for hashing. If I know the key, I can get the exact location of the value in the list. So index, much more appropriate cases for this. So hashing. So I can call this as a hash table, hash list, and the value. I need some kind of function that compute this index value. There's something called hash function. We're going to take a look at very simple hash function. What might be the very simple hash function? We can simply use a modular. Where do we use a modular for implementing list? I think we use that for when we implement a circular queue, right? Circular queue. And then start and bottom is putting together. The reason that we use a modular is make sure the index value doesn't go out of the total size of the list, right? Similar idea. Ideal hashing cases. Ideal hashing cases. If a pair P has a key value, the key K, F is a hash function, the function that computes something called index values, whatever you want to call it. Then P is stored in the position of Fk in the table. 어디 갔니? And this P telling me where it is. For example, it's a memory location, memory address of where it is. This is my key. If I've given a key, I define certain hash function. The value that I get, I can directly access the actual value that I'm looking for. Where it is. Just tell me where it is in the list. So Fk here is a hash function to it. That's what it says. Hash table is used in many real-world applications. Like I mentioned in the beginning of the class, George was mentioning there is maybe a password can be accessed using this hash functions. Pretty much everything. When you try to access the web servers, when you try to go into naver.com, naver.com's server recognize you computing your own hash key values, and they allow to access their web servers and their contents like that. Many, pretty much everything. Pretty much everything. And also, if you can break a hash key, later there's a danger of using this hash key because there might be a same hash key with the two different values or something like that. There's a duplicate cases. If you can break this hash functions, then it's something like you can hack into someone else's system. 해킹할 때 나오는 게 가장 쉬운 얘기로는 해시키 펑션을 깨는 거 같은 거예요. 해시키 펑션을 깬다니까 수학 해시키라고 나와봐야 수학 공식이에요. 수학 공식에서 잘못하다가 다른 값을 줬는데 같은 해시키가 나오는 경우. 키가 다른데 P가 똑같아. 그래서 똑같은 데 가리키면 말이 안 되잖아요. 다른 걸 가리키고 있어야 되는데. 그런 경우를 만들면 가끔가다 시스템이 죽어버리는 경우가 있어요. 그러면 그 시스템에 들어갈 수 있는 경우가 있어요. 지금도 많이 하고 들어갈 수 있는 경우보다는 뭐 아예 시스템을 다운시켜버리는 경우. 그럼 뭐 여러 가지 경우. So it's a typical way of hacking stuff is also having a meaning of you know how to break a hash key, hash function. That's one of the ways of doing it. So there's many real-world applications. I'm going to show you one. Hash table operation, search, compute Fk and C, and a pair exists. So I give you some keys and I put that into my hash function, the value I got, whether it exists in my hash table. Insert, compute Fk, and delete the pair, the place in that position. I try to add in new elements in the hash table. So with that value, I come up with my own hash key and find out where to store it. Then that's my addition part. So it's very similar to the dictionary, right? delete, compute FK, delete the pair in the position. In ideal situation, hash table search, insert, delete takes a constant because hopefully this function gives you exact location of where to put it, where to delete it, where to search. Order of n. Order of 1, constant. Examples is given 10.6 and 10.7. Pretty much same example that I discussed. I think it's part of that example they mentioned. Ideal hashing examples. Ideal means no trouble, everything will be working fine. So pairs. These are the pairs that I wanted to add into my hash tables. So hash table, I'm going to call it as HT, the size of 8, 0 to 7, the size is 8. So 22A, 33C, 3C is 3D, 72E, 85F. 22 is key, A is value, I guess. Hash function, hash table is that, B is 8, where the B is the number of positions in the hash table. So I have 8 positions to put it for the elements. And I'm going to define my hash function in here as a key modular B, total size of the buckets, total size of a list. So I'm going to key 22 modular 8. What's a 22 modular 8? What's the value? 16 빼면 22에 16 빼봐 얼마야? 6. 6. 6. Position 6, I'm going to put 22, 8. Position 6, put 22, 8. Okay, 32 modular 8. 33 modular 8. 4, 8, 32. 1, right? Position 1, 33C. So next time I try to find out my value of a key 33. I do the exact same thing. 33 modular 8, that gives me 1. Go into position 1, my value is C right away. Okay. So that is my very simple hash function right there, right there. Why do they say it's ideal cases in then? Probably there's no duplication in the same position. Maybe no 2 other elements will be asking for the same position. If I add, in that table, if I add, for example, I wanted to add extra ones, 1G. Modular, my key function is F1, but 1 modular 8, which is B. This gives me what? 1. But I look for 1. It's already some of the elements is in here. What do you do then? 똑같은 게 키는 하나인데, 포지션 하나인데, there's 2 elements. Try to add it in. What's happening then? 몰라. That's right. Yeah, that's correct. At this point, we shouldn't know what to do yet. So in this case, ideal case, no elements will be asking for the same position in here. But there will be a case, many cases that you will be asking for a spot, but the same key value, same hash key will give you the problem of where to add. What if you try to add in 8, 9 elements into this bucket size of 8, right? Problem like that. Only 8 spots, but I like to add one more, 9 elements in it. I don't have any other spots left like that. Those are another situation to consider. But in this slide, ideally everything is so nicely adjusted, then no one else will be asking for the same position in the list. What can go wrong? I just mentioned something called collision. Collision is what? In the car accident, they collide together. 뭐지? Collision, 부딪히는 거. They collide. in that example, of course I already give 1G, but in that example, where does 25G goes? 25 modular of 뭐야? 8, 3, 4, 24, 1. Where does it go? The home bucket for home bucket, the home bucket means where it should be going into, the location of that elements in the list. Home bucket, I'm going to call it as a home bucket for 25G, is already occupied by 33C. This situation is called a collision. We just ran into a case for something called collision. They collide together, fight for a spot. The key that have the same home bucket is called synonyms. I never call that as a synonyms. Collision is usually fine. Collision is usually fine. 25 and 33 are synonyms with the respective to hash function that is in use. When I was speaking about this hacking and stuff, some hash functions, our hash function is really easy ones, like modular 8. It's very easy. Some hash functions, they say, they guarantee that they will not give a duplicate values. And they use that hash function for a long time. At some point, some people find out that they can break the hash key, hash function. It means they find a combination that the same hash function will give the same value, which creates a collision in the system. That is something that is same meaning as breaking the hash keys, a hash function. In Korean briefly, 어떤 이렇게 hash function들은 복잡하겠지. 저거보다 복잡할 거 아니야 수학식인데. 근데 이렇게 많이들 만든 사람이 이거는 한 1000만 개 컨비네이션을 넣어도 절대 똑같은 키가 나오지 않는다고 계산을 다 해서 증명을 다 해서 사람들이 그걸 믿고 이렇게 썼는데 한 10년, 20년 쓰다 보니까 어떤 사람이 얘랑 같이 넣으니까 똑같은 거 나오는데 이렇게 해갖고 알려져갖고 그럼 해시 펑션이 망가진 거예요. 근데 시스템에서 아까 얘기한 웹 서버나 이런 데서 다 해시 펑션을 써. 그래서 이 사람이 이 프로그램에서 이 해시 펑션을 썼는데 요거랑 동시에 하면 이거 깨지는데 안 거야. 그래서 그 웹 서버에다가 똑같이 동일한 키를 보내는 거야. 그럼 순간적으로 웹 서버가 깨지는 거지. 떨어져 버리는 거야. 죽어버리는 거야. 어떻게 메모리가 소위 말해 메모리 펑 난다고 메모리가 막 난리가 나갖고 죽어버리는 거야. 그렇게 많이들 해킹도 하고 하죠. 그게 해시키 깬다는 게 그런 의미로도 많이 써요. So you create a collision, intentional collision, and that's one way of looking at it. Again, our hash function here is very simple ones. There are very difficult hash functions out there that is proven that they will not give any other duplicate for billions of different combinations. But I think there's no guarantee nowadays. Someone always find a way out to break that hash function in it. Overflow. So once you have a collision occurs when a home bucket for a new pair is occupied by a pair with a different key. An overflow occurs when there is no space in the home bucket for a new pair. Collision happens, they try to fight for space. Obviously there is no spot to hold both of them. That's something called overflow. Overflow, well, what is overflow? They usually draw this cup, water. I pour more water in, water spills, overflow. There's no memory space to add that in. If that happens, that's the exact same cases for buffer overflow. If you go into Microsoft website for updates and stuff, they usually differ. Security vulnerability, buffer overflow. They had some problem in their program that there at some point the list they have within the program doesn't have any spots for additional elements in it. Also create a problem. Program crash, blue screen, buffer overflow. Something like that is happening. So collision and overflow When a bucket can hold only one pair, collision and overflow occurs together. If there is only one spot, you have a collision, then it's basically an overflow also happening. Right? Needs and methods to handle an overflow. We haven't, but by looking at this picture, what can you do? What can you do? If you have a collision happening, I like to add another elements in the same position. What's your options? Just looking at the graph. Huh? 어떻게 하면 될까? Very dumb and simple solution, maybe. You can add a pointer, I don't know. Start adding a pointer like this. Maybe. That's the one way. Or you change the position within it. Go. We're going to take a look at for linear probing and it's like open hashing like solutions. So we're going to take a look at the solutions to solve this type of situations. 잠깐. About that real world examples for hashing. That's why I download this BitTorrent here. I'm gonna show you where this hashing is used, more real world applications of this hashing. So in order to have those programs ready, they have to come up with a way of not to collide each other. A duplicate key may be a problem like that. So techniques be used in those BitTorrent and other similar programs. We're not going to discuss it, but I just want you guys to see the real-world examples of using hash in real life. Okay, I'm going to call out the attendance now. Any other questions for today? 질문. 수요일 Wednesday가 뭐지? Wednesday 축제라고? 내일하고 내일 모레?